Thanks for joining me to follow up the lecture on solid-state physics, and this time we are about to start our journey on the chapter 4, which considers the thermal properties of the lattice. So I will just give a brief introduction on the chapter 4 in this lecture, and I will then, in the upcoming lectures, I will break the chapter into a part, and I will go through the other lectures and other topics at a time. But before we get started, before I actually go into the mathematics that helps us to understand how these lattice vibration can take place, and that will be covered in section 4.1, so essentially here. And before we go into the heat capacities of the lattices, so once we have realized and calculated that how can we actually consider, how can we calculate mathematically how these lattice vibrations can store energy in a system, then once we know the math, then in here we will progress and we will actually calculate the heat capacity of the lattice. And here mainly we will use the Debye model, which was the first approach of calculating a heat capacity that actually was quantum mechanically correct and also complied with the experiments that had been performed both at the high temperatures and at the low temperatures. So that's the kind of main motivation we have on this course, so that we want to show how this approach, when we are dealing with crystal lattices, so atomic lattices that are periodic, how we can actually take use of this formulation and then do something useful with it. And after we have covered this, after we know how different materials store energy, and we have calculated the heat capacities, then we go to point 4.3, which is about thermal conductivity of solids. And here I will really focus on the lattice contribution on thermal conductivity. And this is then the approach that helps us to understand how different dielectric materials or semiconductors can conduct thermal energy. And then finally, we will go in section 4.4, a little bit about thermal expansion, and I will try my best to elucidate it to you in there, how the microscopic contributions that we so much like to focus here on this course can also form an understanding of these macroscopic effects. So this is the rough outline we have, and I will first in 2 slides go in a little bit more verbose regarding the motivation for the chapter. So essentially, like I said already, what we want to do in this specific chapter 4 is that we want to form an understanding that explains us what are the thermal properties of solids. That's our main motivation, what we want to achieve during this chapter. And especially what we want to do is that we want to understand dielectric materials, like for example, diamond, is a good example of a dielectric material. And similarly, semiconductors, such as silicon, Cg compounds, germanium, if we mention some examples. Other example materials that we could consider here, like dielectrics, so of course, sodium chloride, that's another material we are many times mentioning during this course. So these are the types of materials we want to focus now into. And why we do this distinction and why we do not consider metals here is that they will be treated a little bit in the next chapter. And the reason for that is that the thermal properties, for example, the thermal conductivity and also the thermal capacity, how metals store heat, thermal energy, and how thermal energy is being transported in metallic objects, they are also affected by conduction electrons. And in dielectric materials and in semiconductors, we don't really have that much of conduction electrons. Depending, of course, on the doping of a semiconductor, we may have a little bit of conduction electrons or holes. So that's the kind of subtlety here. But roughly put, with metals, we have conduction electrons, and with dielectrics and semiconductors, we do not. And this is the distinction we want to make in our approach right now. We want to kind of focus first on another contribution into the thermal properties, and then after that we go forward and start looking at the other contributions. So what happens when we also include possibility of having free electrons, conduction electrons in our piece of a solid. So basically, two main contributions exist when we are looking at the thermal properties. And the first one, and this is really the focus we have here in chapter 4, these are so-called lattice contributions. And here we mainly apply these into the dielectrics and semiconductors. And this is in fact the main contribution in such materials. And this is arising from the reason that we don't really have free electrons in dielectrics and semiconductors, and then we do not really have a large contribution because of that. And here, let us remind yet again that we do have conduction electrons, free electrons in metals, and then in these cases, we should also take those into account when we would be estimating what are the heat capacities of metals and what are the thermal conductivities of metals. But this is what we do not do much, or in essence, we do not do at all in this chapter, but we will first focus on the lattice contributions. And after we have done that, we will progress forward. And after the upcoming chapter 5, then after that, we start understanding that, okay, these free electrons may also play a role in thermal properties of solids. So, like I said many times already, we really deal with the lattice contributions. And I'm sorry that I'm repeating myself, but I just want to make it absolutely sure that what we will be speaking here, so that you are not confused during the progression of the course. And what we will do is that we will really develop a mathematical treatment. And this is what we will do in the first subsection, so in 4.1. And then with this, we really understand lattice vibrations, what they are, how they emerge, and what affect their properties, and all these things. And this is the main mathematical tool we need to really understand then what will be the macroscopic thermal properties of solids. So this is what we will do. We want to understand lattice vibrations, and these are also known as phonons, due to the fact that they're actually like discretized in nature, and this will be our main focus in the next few lectures. And after that, we will apply this concept of phonons, and we will calculate and understand what are the heat capacity contributions that are associated with this lattice of atoms, and that will be the main focus of section 4.2. And then after this, we will apply the treatment to macroscopic phenomena. And mainly here, we will look into the thermal conductivities of dielectrics, and then expansion of solids, so essentially thermal expansion. So these will be our chapters 4.3 and 4.4 subsequently. So this is our outline for the chapter 4, and I will next start with another lecture on the actual main mathematical derivation that we will start. So I will start with 4.1 next. So thanks for listening this, and please have patience. And on the other hand, have enough time to follow through this material, because this is a basis that we will use also in the subsequent chapters on this course. So this is not just about thermal properties of solids, but this is also a kind of one of the main building blocks that we will use in this course. So thanks, and bye-bye.